Welcome back to the deep dive. Today is a massive one. We are going fully into Simplified UPSC by PPP mode.
That's right. We're taking the source material, specifically NCERT Class 6, Chapter 3, and we're effectively wringing every single drop of value out of it. We are going deep.
Now, before we get into the heavy lifting, and trust me, we have a lot of heavy lifting to do regarding orbital planes, solstices, and all that tricky geometry. I want to start with a feeling. I want you, the listener, to do something for me right now.
Okay.
Wherever you are, unless you're driving, in which case, please keep your eyes on the road and hands on the wheel. But if you can, I want you to sit perfectly still.
Freeze?
Exactly. Don't move a muscle. Maybe hold your breath for a second. Just exist.
It's harder than it sounds, isn't it? You feel that urge to twitch, to move.
You do, but here's the reality check, and this is the immediate hook for today's session. Even if you think you are freezing like a statue, you are currently spinning at a speed of roughly 1,000 miles per hour. And at the exact same time, you are rocketing through the vacuum of space at 67,000 miles per hour.
It sounds like the opening monologue to a high-budget sci-fi movie, doesn't it?
It does.
Yeah.
But it's not. It's actually just page 1 of your geography textbook.
And that is the paradox of this specific topic. It's Chapter 3 of Class 6. The title is Motions of the Earth. And because it's Class 6, a lot of aspirants, especially those prepping for UPSC, they look at it and think,
Oh, come on! I know this!
exactly. Earth spins, sun rises, winter comes, summer goes. I'll skip it. I need to study the complex stuff, the economic survey or something.
And that arrogance, that's exactly where they lose marks.
Precisely. Because the UPSC prelims doesn't ask, does the Earth spin? That's way too easy. They ask about the specific geometry of the tilt, the nuance of the solstices relative to the tropics, and the variation in daylight hours at very specific latitudes. If you don't have that conceptual clarity, the mechanics of the machine, you will fall into the trap options every single time.
So that is our mission today. We are going to provide a comprehensive, high-yield breakdown of these motions. We're going to decode the geometry, tackle those scary terms that people always mix up, and link it all to actual previous year questions.
We're going to build the machine of the seasons from the ground up, bolt by bolt.
But first, a very, very crucial message for the community that makes all of this possible. If you are finding value in this deep dive, if these sessions are helping you simplify your prep, and frankly, saving you hours of reading time, we humbly request you to subscribe to the Simplified UPSC by PPP channel.
It really does support the mission. It tells us we're on the right track and helps make this high-quality education accessible to everyone.
And for those of you who are capable and want to help us keep the lights on and the research team fed, please consider supporting us on Patreon. And a massive, warm shout-out to all our current supporters. You guys are the engine behind this ship. We literally could not do this without you.
Absolutely. Thank you so much for keeping us going.
Also, some quick housekeeping. Please like the video and leave a valuable comment. It boosts retention, it helps the algorithm find other aspirants who are, struggling with geography, and frankly, we love reading them. Now, regarding resources, because I know you're going to ask, where are the notes?
We have you covered, don't worry.
Resource alert. Free notes with practice PYQs, that's previous year questions, are available right now on the public Telegram channel. Go grab them. But if you want the full experience, if you want access to all the videos in this series at once, plus the organized premium notes, which have the detailed summaries, extra PYQs, and model mains answers.
That's the holy grail package for the serious aspirant. It's everything in one place.
Then you need to join the private Telegram library. The instructions are simple. Just DM us on the public Telegram channel to join. Okay, housekeeping done. Let's look at the map.
The roadmap for today.
We have 4 main stops on this journey. Part 1 is the spin. We're talking rotation. Part 2 is the journey. That's revolution. Part 3 is the mechanics of seasons, solstices and equinoxes, all the good stuff. And Part 4, the most important part, the exam, connecting it directly to UPSC PYQs so you can see how this theory translates to marks.
Right. Let's start with the spin.
Part 1, the spin rotation.
Okay, let's start with the definition. It sounds basic, I know, but let's be precise. Rotation is the movement of the Earth on its axis.
The text uses a few analogies here to help us visualize it. It talks about a spinning top, which I think everyone gets.
Or a potter's wheel. That steady centering spin that creates a blur. That's a great image for it.
But to really understand this, we have to visualize the axis. I think this is where the first misconception happens for a lot of people. When we look at a globe in a classroom, the plastic ones on the teacher's desk, there's a literal metal rod sticking through the top and bottom.
Right. It holds the globe in place so you can spin it. But in reality, obviously, there is no giant metal pole impaling the planet.
That would be problematic.
Very. The axis is an imaginary line. It runs through the North Pole, down through the center of the Earth, and out the South Pole. It's the pivot point.
The insert book suggests a let's do experiment here to help students and, let's be honest, adults too, visualize this. It says take a ball or a big round potato.
A potato. I love that.
Yes, a potato. I love the accessibility of that. It's like, go to the kitchen, find a potato.
It works, though. I mean, it's an imperfect sphere, just like Earth. A bit lumpy.
Exactly. So you take this potato and you pierce a knitting needle through it. That needle represents your axis. You can spin the potato around that needle, that motion, that is rotation. But here is the catch, and this is the high yield point for the exam. If you were holding that potato representing Earth, strictly following the laws of our solar system, you wouldn't hold the needle straight up and down.
No, you would have to tilt it. It's not perfectly vertical.
This brings us to the geometry of the tilt. And this is where I see people get confused with the numbers. There are two numbers thrown around in the textbook: 66.5 degrees and 23.5 degrees. Can we just clarify this once and for all? Because I feel like students memorize one and then get asked about the other.
This is crucial. This is a classic trap question you have to ask yourself. Tilted relative to what? I mean, the Earth is floating in space. There is no up or down in the vacuum of the cosmos. So we need a reference point to measure an angle against.
Okay, so what is our reference point?
The orbital plane.
Let's unpack that term. Orbital plane. It sounds very technical.
It's actually quite simple if you visualize it. Imagine the Earth is sitting on a massive flat glass table. The sun is in the middle of this table. The Earth slides around the sun on this glass surface year after year.
Okay, I'm visualizing the glass table. The path is on the table.
That glass surface is the orbital plane. It's the flat plane formed by the Earth's orbit. Simple as that.
Got it. Okay.
Now, go back to your potato with the knitting needle. Imagine you set that potato on the glass table. Is the needle sticking straight up at a perfect 90-degree angle to the glass table?
No, the source says it's inclined. It's leaning.
Right. It's leaning over. It's like the potato is tired. The angle between the glass table, the orbital plane, and the axis, the needle, is 66.5 degrees.
Okay, so if I took a protractor and measured from the table surface up to the needle, that angle is 66.5 degrees.
Correct. That is the angle of inclination with the orbital plane. That's the key phrase.
Then where does the 23.5 degrees come from? Because that's the number everyone remembers, the Earth's tilt.
That comes from the vertical. Imagine you drew a line straight up from the glass table, a perfect 90-degree vertical line, like a little pillar standing straight up from the plane.
Okay, a vertical reference line.
The Earth's axis is tilted 23.5 degrees away from that vertical line.
Ah, I see. So it's just basic geometry. A right angle is 90 degrees. If you take away the 66.5 degrees from the table, what's left is 23.5 degrees from the vertical. 66.5 plus 23.5 equals 90.
Exactly. It's the same tilt, just described from two different reference points.
It's like describing a hill. You can say it rises 30 degrees from the ground, or you can say it's 60 degrees away from a vertical wall. Same hill.
Perfect analogy. But here's the warning. In a preliminary exam question, they will trap you. They will ask, what is the angle of the Earth's axis with its orbital plane? And option A will be 23.5 degrees.
And if you're rushing, or if you just memorized Earth tilt equals 23.5, you click A.
And you get negative marks. The answer to that specific wording is 66.5 degrees. You have to read the question to see which angle they are asking for. Are they asking for the tilt from the vertical or the inclination from the plane?
That is a classic trap. I'm so glad we spent time on that. Okay, so we have this spinning potato and it's leaning over. Now, because the Earth is a sphere, only half of it can face the sun at any one time.
Right. The side facing the sun has day. The side facing away has night. Pretty straightforward.
And there is a line that divides them. The text calls this the circle of illumination.
Yes. And here's another visualization challenge for you. The circle of illumination is basically the shadow line. Imagine you are in a dark room holding a basketball. You shine a flashlight at it.
Okay, flashlight is the sun. Basketball is the Earth.
The line between the lit half and the dark half is the circle of illumination. Now, here is the key question. Does that shadow line line up with the axis, with the knitting needle in your potato?
Well, The axis is tilted. We just established that. It's leaning over.
Hmm.
But the flashlight, the sun's just shining straight at the ball. The shadow would be straight up and down, right?
Exactly. The circle of illumination is always vertical relative to the sun. It is strictly perpendicular to the sun's rays, but the axis is tilted.
So the axis and the circle of illumination, they cross each other. They don't line up.
They cut across each other. They do not coincide. That is a very specific statement in the NCERT. The circle does not coincide with the axis.
And that misalignment is why the North Pole can be inside the circle of illumination, having 24-hour daylight, even while the rest of that side of the world is turning into night.
Precisely. If the axis and the circle coincided, every single place on Earth would have sunrise at 6 a.m. and sunset at 6 p.m. every single day forever. The fact that they don't coincide is what gives us variation in the length of days.
That is a great distinction. The axis moves with the Earth's tilt, but the circle of illumination is determined by the sun's position.
Spot on. You've nailed it.
So what are the direct consequences of this rotation? Let's just list them out.
Well, obviously day and night. That's the primary cycle of our lives. Also the direction. Earth rotates from west to east.
Which is why the sun appears to rise in the east and set in the west. It's like being on a train. If the train moves forward, the trees outside look like they're moving backward.
Exactly. And this period of rotation, about 24 hours, is called the Earth Day. That is the specific term the source uses. It represents the daily motion of the Earth.
Now, the source poses a what-if scenario. And I love these thought experiments because they force you to understand the mechanic by breaking it. What would happen if the Earth just stopped rotating?
It's a terrifying thought. So let's assume the Earth stops spinning, but it keeps orbiting the sun.
Okay, so one side is locked facing the sun permanently, kind of like how the moon is tidally locked to us.
Right. The side facing the sun would experience continuous daylight. It would never get a break. It would just experience continuous compounding warmth.
You would essentially bake.
It would be a frying pan. Temperatures would soar beyond anything habitable. All the water would boil off.
And the other side, the dark side.
Permanent darkness, freezing cold. No solar energy ever reaching it. It would be a ball of ice.
So basically you'd have a burning desert on one side and a frozen wasteland on the other. Not great.
Life as we know it would not be possible. Rotation is what moderates the temperature. It acts like a rotisserie chicken. It ensures both sides get heated and cooled evenly in a 24-hour cycle. It distributes the energy.
That's a vivid image. Earth is a rotisserie chicken. I'll remember that. Before we move on to the next motion, there is a little do you know box in the source about Aryabhata.
Yes, the ancient Indian astronomer. A genius.
He stated that the Earth is round and rotates on its own axis. And he said this. I mean, this was long before the age of modern space exploration.
It's incredible when you think about it. I mean, stand on the ground, everything looks flat, it feels like the ground is still and the sky is moving. That's our direct experience.
Right. It's intuitive to think we are the center of everything.
So to look at the stars, to do the math, and to deduce that we are the ones spinning, that requires a massive leap of logic and mathematics. It really just shifts your perspective on how advanced ancient Indian science actually was. He was calculating this while much of the world was, in the dark, literally and figuratively.
It really does. Okay, so we are spinning. That's motion number one. But we are also traveling. Let's move to part two, the journey revolution.
Revolution. This is the second motion. This is the movement of the Earth around the sun in a fixed path or orbit.
And the source is this takes 365 and a quarter days. 365 and a quarter days.
Right. 1 year. But here is where we get into the messy math of our calendar, the leap year logic.
I think everyone knows that a leap year happens. We get an extra day in February. But explaining why it happens can get a bit jumbled sometimes.
It's actually a bookkeeping problem. The Earth doesn't care about our clocks or our calendars. It takes 365 days and roughly 6 hours to complete one full circle around the sun.
But we can't have a calendar with a quarter of a day at the end. I mean, you can't have New Year's Eve start at 6:00 p.m. the next. It would be
chaos. Our entire system of timekeeping would fall apart. So, for the sake of convenience, for simplicity, we define a normal year as 365 days. We ignore the 6 hours.
We just pretend they don't exist.
For a while, yes. We put them in a sort of cosmic savings account. So, year one, we ignore 6 hours.
We ignore another 6 hours. Now we've saved up 12 hours.
Another 6. Total saved 18.
Another 6. And what's our total? 24 hours.
We have saved up a full day.
Exactly. So every fourth year, to balance the books, we take that surplus day that we've saved up and we stick it into the shortest month, which is February.
Which is why February usually has 28 days. But in a leap year, it has 29. And that makes the whole year 366 days long.
It's a clever accounting trick to keep our seasons aligned with the calendar. If we didn't do this, our seasons would drift by about a day every 4 years. After a few centuries, the calendar would say December, but the weather outside would feel like June.
That would be incredibly confusing. Imagine planning a winter holiday and getting a heat wave just because we forgot to count the 6 hours.
Exactly. So the leap year anchors our calendar to the solar reality.
Now let's look at the path itself, the orbit. The source is very specific about the shape.
It's an elliptical orbit.
So not a perfect circle, it's slightly elongated like a flattened circle or an oval.
Correct. But here is the most critical part of revolution. It's not just that we are moving, it's that while we are moving, the tilt we spent all that time talking about, it stays constant.
The source says the axis remains inclined in the same direction.
This is the concept of axial parallelism. Though the NCERT doesn't use that big word, it just means the axis doesn't wobble back and forth like a confused spinning top. It points to a fixed spot in the sky. For us, that's Polaris, the North Star.
Can we use an analogy for this? Because visualizing a fixed direction while you're moving in a giant circle is a little tricky for the brain.
Sure. Let's use a bonfire analogy. Imagine you are walking around a big bonfire in the center of a field. That's the sun. You are holding a flagpole. That's the Earth's axis. And way off in the distance, there's a very tall specific tree. That's the North Star.
Okay, I'm walking around the fire holding my flagpole, and I'm keeping the pole pointed at that distant tree. I'm not pointing it at the fire, I'm pointing it at the tree.
Exactly. Now, when you are on one side of the fire, pointing at the tree means the pole is leaning towards the fire.
Right.
The fire is between you and the tree.
Right.
But when you walk to the opposite side of the fire, 6 months later in our orbit, you are still pointing the pole at that same distant tree. But because of where you are standing now, the pole is leaning away from the fire.
Ah, I see it. The pole itself didn't change its orientation relative to the tree, but its orientation relative to the fire completely flipped. One moment it was leaning in, the next it was leaning out.
That is exactly what causes the seasons. It's the combination of the revolution around the fire and that fixed tilt towards the tree. If the pole wobbled and always pointed at the fire, we wouldn't have seasons. It's that constant direction that matters.
This leads us perfectly into part 3, the mechanics of seasons. The outline calls this the recipe for seasons, which I like.
The recipe has 2 essential ingredients. You can't leave either one out.
The Earth revolves.
The Earth is tilted in a fixed direction. If you remove either one, the recipe fails. You don't get seasons.
Let's play that out, just to be sure. If the Earth revolved but stood straight up 0 degrees tilt.
No seasons. Every day would be 12 hours of light, 12 hours of dark, everywhere. The temperature would drop as you went from the equator to the poles, but it would never change throughout the year. It would be a permanent spring or autumn, depending on where you lived. Kind of boring, actually.
And if the Earth was tilted but didn't revolve, if it just sat in one spot spinning?
Then one hemisphere would be stuck in permanent summer and the other in permanent winter. Forever. Revolution is what allows us to swap places and give each hemisphere a turn.
Okay, so let's break down the 4 main positions mentioned in the source. This is the core of the chapter, and this is where the exam questions really come from. We'll start with the summer solstice.
June 21st.
Describe the mechanics for me. What is the North Pole doing on June 21st?
On June 21st, the North Pole is tilted towards the sun. It's bowing down to the king, you could say. It's leaning in.
And because it's leaning toward the sun, where are the sun's most direct vertical rays hitting the planet?
The rays fall directly, vertically, on the Tropic of Cancer. That's the line at 23.5 degrees north latitude.
And when rays fall directly, they carry more heat. They're more concentrated.
Much more intense heat. Think of it like a flashlight beam again. If you shine it straight down on a table, you get a small, bright, intense circle of light. If you shine it at an angle, the light spreads out over a larger area and gets weaker, dimmer. On June 21st, the northern hemisphere gets that concentrated, intense beam.
And let's look at the duration of the light. Because the North Pole is tipped forward into the light spills over the top of the planet.
That's a great way to put it. It spills over. It means places beyond the Arctic Circle are bathed in sunlight for 24 hours a day. The sun never sets. It just circles the horizon.
The famous land of the midnight sun.
Exactly. You get continuous daylight for about 6 months in those extreme polar regions. But for the rest of us in the northern hemisphere, like in India or Europe or North America, June 21st is simply the longest day and the shortest night of the entire year.
Meanwhile, what's happening in the southern hemisphere? In Australia or South America?
The exact opposite. If the north is tilting towards the sun, the south must be tilting away. It's hiding from the sun.
So the rays are slanted there, weaker, less heat.
And shorter days. It is winter in the southern hemisphere. Their nights are longer than their days.
Okay, that's June. Now let's fast forward 6 months. The Earth swings all the way around to the other side of the solar system. We're at December 22nd. This is the winter solstice.
Now the geometry flips. Remember our bonfire? We're on the other side. The North Pole is still pointing to that distant tree, but now that means it's tilting away from the sun, and the South Pole is tilting towards it.
So who gets the direct vertical rays now?
The Tropic of Capricorn. That's the line at 23.5 degrees south.
So the southern hemisphere is getting that direct blast of solar energy.
Correct. So it is summer down there. They are having their longest days and shortest nights.
And for us in the northern hemisphere?
We are tilted away. The sun is low in our sky. The rays are slanted, spreading the heat out very thinly over a large area. It's winter. Our nights are long, our days are short.
The source mentions a great real-world example here. It asks, do you know that Christmas is celebrated in Australia in the summer season?
It's such a jarring image for those of us raised on Western movies with snowy Christmases. We picture reindeer and snow and hot chocolate. But in Australia, it's a barbecue on the beach.
Santa Claus on a surfboard?
Literally. But astronomically, it makes perfect sense. December 25th is just a few days after the winter solstice for the Northern Hemisphere, which means it's the summer solstice for them. It's the absolute peak of their summer.
So we have the extremes, tilted toward, tilted away. But twice a year, we hit a transition point, a middle ground, the equinoxes.
March 21st and September 23rd.
What is happening to the tilt here? How is it positioned relative to the sun?
This is the sideways position in our orbit. In these two positions, neither pole is tilted towards the sun. The axis is kind of sideways relative to the sun. Imagine the sun is looking straight at the Earth's waist, the equator.
So the direct vertical rays fall on the equator.
Exactly. And the result is that the circle illumination passes right through both poles. So the whole Earth, north and south, experiences equal days and equal nights. Hence the name equinox, which means equal night.
And these are the seasons of transition, spring and autumn.
Right. It breaks down like this. On September 23rd, the northern hemisphere is starting to tilt away from the sun. It's cooling down. That's autumn or fall. We are heading towards winter. The south, meanwhile, is starting to tilt towards the sun, so it's spring for them. They're warming up. Then on March 21st, it's the reverse. The northern hemisphere is now tilting back towards the sun. We're warming up, so it's spring. The south is tilting away, so it's their autumn.
It's this beautiful rhythmic dance. Rotation gives us the beat, the 24-hour day. Revolution gives us the melody, the 365-day year. And the tilt gives us the dynamics, the changing seasons.
That is a very poetic way to put it, but it's absolutely correct.
I try. But now we have to get practical. The listener isn't just here for poetry. They're here for points on an exam. So, part 4, connecting the dots. We need to see how this theory translates to marks in the exam hall.
Let's look at the source material provided, specifically that PDF file, 13csp1.pdf. This contains a question from the 2013 Civil Services Prelims, a real question.
Okay, this is question 11 in that particular set. I'm going to read it out slowly. Listeners, try to answer this in your head before we spoil it. Variations in the length of daytime and nighttime from season to season are due to, and here are the options. And here are the options. A, the Earth's rotation on its axis, and here are the options. B, the Earth's revolution around the sun in an elliptical manner, and here are the options. C, latitudinal position of the place, and here are the options. D, revolution of the Earth on a tilted axis.
Now, this is a beautiful example of a tricky UPSC question. Why? Because options A, B, C, and D are all true statements. They are all scientifically correct facts.
Right. They are all facts about the Earth. Earth does rotate on its axis. Earth does revolve elliptically. Latitude does determine climate. Earth does have a tilted axis.
Exactly. So you can't just pick the one that is true. You have to pick the one that causes the specific phenomenon in the question, which is the variation in day length. This is an attribution question. It's about cause and effect.
Let's eliminate them one by one. Option A, the Earth's rotation on its axis.
Rotation causes day and night to happen. It creates the cycle of light and dark. But does rotation by itself explain why the day is longer in June than in December? No. The rotation speed is constant. If it were just rotation and no tilt, days would always be the same length. So A is out. It's a necessary condition, but not the cause of the variation.
Okay, Option B, the Earth's revolution around the sun in an elliptical manner. This is a common trap. People think, oh, ellipse means sometimes we are closer to the sun, sometimes further. Maybe that changes the day length.
That's true. We have perihelion when we are closest and aphelion when we are furthest. But that distance affects the intensity of the heat we receive slightly, not the length of the day. If the axis were straight, even with an elliptical orbit, the sun would rise and set at the same time every day. The geometry of the shadow wouldn't change. So B is out. It's a red herring.
Good point. Okay. Option C, latitudinal position of the place.
Latitude is important. It determines the magnitude of the variation. At the equator, there's almost no variation in day length. It's always around 12 hours. At the poles, there's total variation, from 0 to 24 hours of daylight. But latitude is just a location. It's not the cause of the seasonal change itself. It's the stage, not the actor causing the play.
Which leaves us with D.
Revolution of the Earth on a tilted axis. You need both. The tilt is what orients one hemisphere more towards the sun, creating the potential for longer days, but it's the revolution that changes which hemisphere is oriented that way over the course of the year. It requires both working together. That is the engine of seasonal variation. That is why D is the correct answer.
See, this is why we do these deep dives. It's not just about knowing the facts. It's about the logic of elimination. You have to understand the mechanism to rule out the distractors that are true but irrelevant to the question being asked.
Absolutely. The examiner is testing your conceptual clarity, not just your memory of a textbook line.
And looking at the mains papers, we have sources from 2014, 2016, 2020. The instructions are always very strict. I'm seeing phrases like, content of the answer is more important than its length.
That's explicitly written. They don't want fluff. They don't want you to write a novel. If they ask you to explain the mechanism of the summer solstice, they don't want a poem about summer flowers or how nice the weather is. They want the geometry. Tilt is 23.5 degrees from the vertical. North pole leans towards sun. Rays fall vertically at the Tropic of Cancer.
Longer days and more direct insolation in the northern hemisphere. Boom. Done. That's it. You get the marks. Crisp and to the point.
Before we wrap this up, I want to briefly connect this to Chapter 8, India Climate. We have a source on that too. It's a great way to bring this global concept down to a local level.
This is the so what for Indian students. We've talked about these global motions, but how does that feel on the ground in Delhi or Mumbai or Chennai?
Chapter 8 describes the cold weather season in India, or winter. Why is it cold in January in northern India?
It's because of everything we just discussed. In January, we're just past the winter solstice position. The Earth's northern hemisphere is tilted away from the sun. The sun is busy heating up Australia and the Tropic of Capricorn. The rays hitting India are slanted. They're weak. Slanted rays equal less heat energy per square meter, and that equals the cold weather season.
And what about the hot weather season or summer?
By May and June, the Earth has moved in its orbit. The sun's apparent position is marching back north. The rays are falling more or less directly over the Indian subcontinent. The land heats up intensely. The air pressure drops. And that's when you get those hot, dry winds called the Lu sweeping across the northern plains.
So when you feel that Lu wind hitting your face in Delhi in June, you aren't just feeling hot air. You are directly experiencing the geometry of the Earth's 23.5-degree tilt in that specific point of its yearly revolution.
You are feeling the cosmos on your skin. That's a direct physical consequence of planetary mechanics.
I love that. Okay, let's bring it home. Summary time. Let's make this stick.
Okay, let's unpack the key takeaways for your mental cheat sheet.
Rotation is the spin. It causes day and night. The period is 24 hours, and the NCERT calls it the Earth Day.
Revolution is the orbit. It takes 365 in ordered days. That extra quarter day creates the leap year every 4 years to keep our calendar accurate.
The axis is tilted, remember the two numbers, 66.5 degrees to the orbital plane, or 23.5 degrees to the vertical, and crucially, it stays fixed in direction.
Seasons happen because of the specific combination of revolution plus the tilt. Not one or the other, but both.
Solstices are the extremes, when the tilt is maximal towards or away from the sun, June 21 and December 22. Equinoxes are the balance points when the sun is over the equator, March 21 and September 23.
And for our listener, the learner, why should they care about this beyond the exam? What's the big picture?
Because this geometry dictates everything. Everything. It dictates when our farmers sow their crops and when they harvest them. It dictates our festival calendar, why we have harvest festivals like Makar Sankranti or Pongal at specific times of the year. It explains why we eat different foods in different months. It is the fundamental rhythm of life on Earth.
And on a very simple level, it explains why you have to turn on your headlights at 5:00 p.m. in December, but you can be outside playing cricket until 7:30 p.m. in June.
Exactly. It connects the celestial to the daily. It's not just abstract science, it's your lived experience.
I want to leave you with a final thought to chew on. We talked about Aryabhata. He figured out the Earth rotated in the 5th century CE. But just imagine the world before that knowledge was widespread.
When humanity stood on the ground and truly, genuinely believed that the Earth was the fixed, unmoving center of everything, and the massive dome of the sky, the sun, the moon, the stars, was spinning around us to pay homage to us.
That is a very egocentric view of the universe, isn't it? I am the center. Everything revolves around me.
And science specifically, this kind of geography and astronomy, humbled us. It showed us that we are just a rock, tilted sideways, spinning at 1,000 miles an hour, orbiting a pretty average star in a vast, cold darkness.
How does that shift in perspective from being the master of the universe to being a passenger on a spaceship change how we treat our planet and how we treat each other as fellow passengers?
It makes you feel smaller, for sure, but also part of something much, much more elegant and interconnected.
Something to think about until the next deep dive. Once again, if this helped you simplify your UPSC prep, please subscribe to Simplified UPSC by PPP.
And if you can, support the mission on Patreon. Quality education takes real resources, and your support is what keeps this content flowing and free for everyone.
Don't forget the Telegram channels, the public channel for your free notes and PYQs. Go get that 2013 question and solve it yourself now that you know the logic. And the private library for the premium experience. Just DM us on the public channel to join.
Like, share, and comment below. Tell us, which geography topic gives you nightmares? Maybe we'll deep dive that next.
We read every single comment. Until next time, keep learning. And remember, you might be sitting still, but you're going places.
Literally,
Yeah.
at 67,000 miles per hour.